Hello, welcome back to part 6 of our studio supplement for Econ 312. At this point in the class, we're about halfway through the class, and this particular section is going to go over simulation of Taylor rule. But the first thing we're going to do is we're going to load some data, and I'm going to copy and paste some code here. I'm going to give this code to my 312 students. This will be in the Slack channel. If you are watching this outside of my class, but just stumbling across this on YouTube, then feel free to pause the video now so that you can type it out. So the first command is exactly what we've been dealing with for all of our various videos. It's basically a link to the Dropbox file that's got all the data for this class. The second few lines of here create a separate data frame for recessions in the United States starting in 1960 and going to today. These dates are picked from the National Bureau of Economic Research. They identify both the peak and the trough, so either where output stops growing and starts to fall, the peak, or then where output stops falling and starts to grow, the trough. So we have both the beginning and the end, so to speak, of the various recessionary phases within the United States. And these are going to allow us to give some shaded areas or some shaded bars for our time series plots that we're going to make within this video. Now, before we actually execute these lines, like I said, I just pasted that in from my own individual browser, and I'll give that code on the Slack channel for my students. Now, we need to call a package in our library. Now, we could use either the tidyverse package, but really all I need for this particular video is just ggplot2. So we want to make sure we have ggplot2 loaded within our library. We want to make sure that we have our data from the course, on this course that has all the data frames that we'll need for the rest of the course, and then we want to make sure that we load this or execute this recessions.df data frame. And I'm going to actually just click on that so that you can see exactly what that does. It basically is just creating a small, simple data frame where you have some date objects here. You see the column for peak and you see the column for trough. And that's going to allow us, like I said, to draw some recessionary bars that kind of lay in the background for our time series plot. So we'll start here building a ggplot2 object using the ggplot command, and then I'm just going to go ahead and give this the Taylor data frame that we're going to be using to plot here, and we probably should actually look at that. So let's take a look at the Taylor data frame. So what we have here, just as we have for a lot of our other data frames in this, we have a date column. So this is going to give us quarterly observations starting in 1960 and going to, I think, the beginning of 2020. Yes, yeah, the first quarter of 2020. I don't have the second quarter of 2020. As we know, the U.S. economy is exploding, and as a result of that, we see in the second quarter, our first estimates of second quarter GDP at the time of this recording, we saw basically a negative 30%-ish drop in real GDP. That's probably going to get revised. I don't trust that initial estimate. I never trust initial estimates anyway, but I have a feeling that's going to get revised, and that revision won't come out until the third quarter preliminary estimates are due to be released, and they're not at the time of this recording. They're not released yet. So I've left off the second quarter of 2020 in this. Now we also have beside that we have a column for RGDP that stands for real GDP, POT GDP that stands for potential or full employment GDP. These two columns here are created and are used to generate the last column, the gap, which is the output gap, exactly that we talked about in class, as the percent deviation of output from full employment output. So you don't really need RGDP and POT GDP in this. You really need just the gap column. I've done the work for you here, but just keep in mind we generate this from these two columns, taking the log difference and multiplying by 100. Now, in the middle here, we have INT, which stands for the interest rate. This is going to be the effective federal funds rate, aggregated and at the quarterly frequency. And then we have quarterly estimates of inflation. So these are quarterly numbers here that have been annualized. So great. So really, we just need this inflation and this gap columns in order to generate our Taylor rule, but then we also need the INT column in order to compare the Taylor rule to the effective federal funds rate so that we can get a sense of how well it actually fits the data. And then, of course, we need our date column. Fantastic. All right, so like I said, we're going to create a Taylor rule or a ggplot object with the Taylor dataset, and the thing that we're going to put in first is going to be the rectangular area. So we're going to use this geom rect command, and we are going to specify that we want the data, in this case, to be the recessions.df data frame. Great. And then we want the AES commands. And here we have to specify in our rectangle, so to speak, the 4 points. So we need to have both the X-min and the X-max for each shaded area, and then we also have to have the Y-min and the Y-max. And the Y-min and the Y-max, they're going to get truncated anyway, but we'll still specify them nonetheless. So for the X-min, we want to give it the peak. I think peak was just capitalized once. Am I right? Yes. Okay. Fantastic. So peak is just is capitalized once, but not fully here as in like the Taylor object. Again, we have to be very careful with our it's case sensitive, so our capitalization is important. We'll specify X max to be equal to the trough. We will specify Y min to be equal to negative infinity. And then our Y max equal to positive infinity. The positive probably is not nearly as important, but we'll still be explicit nonetheless to avoid any confusion. And then we'll move out of our parentheses for the AES input there, and we will specify the fill. And this will give us the color, and we'll make it just red. Might as well. Sounds like fun. Let's do it. And then we want to specify this additional argument alpha, and this is going to give us the degree of shading, kind of the opacity, so to speak. This, and so we'll limit the opacity as well, so that it kind of operates like a shaded object without any problem. Great. And then we'll specify our geom line that we're after, because we're going to do a plot. And the first thing we're going to do is we're just going to plot inflation. I want to plot just inflation and talk about the inflation dynamics here, because they're so very important to understanding what's happening with the Taylor rule. And so we will we'll plot the date along the x-axis. We will plot actual inflation. Nope, not capitalized, INFL for inflation. Notice I spelled inflation with INFL instead of INF because we have the capital INF here, and that's just kind of confusing. So, and also INFL is lowercase, as we can see from the Taylor object. So again, be careful with the case sensitivity there. And we'll leave that just by its default black color, because it'll just come up as black. And then we will go ahead and specify some labels, just as we've done before. So we'll specify the X label as nothing, because otherwise it'll print date in lowercase and just kind of look really crappy. And then on the Y axis, we'll go ahead and specify that as %. And then for the title, we will say we want, again, that I hate that box that keeps coming up here, autofilling and giving me direction of what to type in. It makes it difficult for the video. My apologies. We will say we have U.S. Consumer Price Index inflation, because that is exactly what that inflation measure is. It's inflation measured via CPI. So fantastic. We are ready to go. Let's execute this and let's see what we get. Ooh, that's pretty. Let me zoom it and make it bigger so we can see it a little bit clearer on the video. All right, so a couple things to note here right off the bat. So even though we specified in the geom rectangular command that the boundaries on the y-axis is positive infinity and negative infinity, the scale of the inflation time series that we're plotting here, it dictates how far up it goes actually within the ggplot function or output. So that ends up being a non-binding constraint. You still have to specify it, but it ends up being a non-binding constraint as you build and layer up this graph. We clearly can see now we have some shaded bars here, the kind of pinkish bars, since we started out red, but we limited the opacity to 25%. Now all of a sudden those red bars look pinkish. And of course, if you want a different color, put it in a different color. That's fine too. But we can see now where the recession starts and where the recession ends. Even though this is given at the monthly interval, it still interlaces them and plots them exactly the way that it should with the quarterly data. So the actual black line is quarterly data, but the recessionary bars are a little more precise. Additionally, because I entered the current recessionary phase that we're seeing as a result of COVID-19 in the United States, it picks up. The NBER has already announced that has started in February of 2020, but has not ended yet. I've gone ahead and just truncated it to the month of, I think it's September. So we have this recessionary bar here, but the data doesn't extend into it, although certainly we are. So that's kind of a visual reminder that our data is kind of truncated, but we're still in a hot mess. Now, so let's talk about inflation a little bit, and this is something that I haven't done in this class, and it's probably worth talking about a little bit. We see some kind of general dynamics here. We've already talked about interest rate data. We talked about the term structure of interest rates in the class, and we know that we had this general upward incline in interest rates from 1960 to 1980, and we certainly see that as well within our inflationary data also. It's not quite as high as it was for the interest rate data, but it still very much is there. So we started to see this kind of upward swing, a whole bunch of increased volatility in the 1970s, and then we start to see we kind of peak out here at the beginning of 1980. After that, we started to see this kind of march downward. This whole area right here that the cursor is circling around, this is what we refer to as the Great Inflation. It's a period of high inflation, high price volatility in the United States. It's caused by a handful of different factors, and we can talk about some of those later on. I won't get into all of those reasons now, but it's largely due to the movements of the Federal Reserve with Paul Volcker at the helm that started to push the U.S. economy into a recessionary phase that pulled this down. This general decline after this peak in the beginning of 1980 is referred to as the Great Disinflation, adequately enough. And then we talk about this area here where things are pretty stable for the most part for the solid 25 years or so as the Great Moderation. So it's an era of the U.S. economy where we had relatively low inflation. Prices were much more stable in that regard, but then we also had exceptional growth in the U.S. economy at that time. This Great Moderation period ends, of course, with the crash of the housing market and the subsequent recession that happened in 2008. We see a really the largest deflationary spike that we've seen post World War II, and then then things kind of mellow out again. A little bit lower though. The average value here is going to be lower than what it was during the Great Moderation, with a couple of deflationary spikes peaking out below zero along the way. So this kind of gives us an indicator of what's happening with pricing data. Now, because the construction of the Taylor rule is the way that it is, the pricing data that we're seeing here in this plot is going to have a disproportionately larger weight on this, and this is reflected in the Fed's preference for the price stability portion of its dual mandate. So we have to understand how inflation works, because these dynamics are going to be superimposed into our Taylor rule with a disproportionately heavy-handed weight on this because of that weighted average component of the Taylor rule mathematically. Great. So we're going to do the exact same thing. I'm basically just going to take this and copy it, because once we've constructed this, we're actually off to the races. So I'm going to copy this whole graph, and I'm just going to paste it down here below, except I'm going to change a couple things. I'm going to leave the first few lines exactly the same, the rectangular components, the recessionary bars, all the same. Instead of INFL for the actual time series, we're going to plot the gap. And then we're going to change the title because I don't want to confuse this. We're going to plot that as, or call that title U.S. output, if I can type, output gap. Great. Now, I'm going to leave the y-axis as a percent because if you recall, we talked about that output gap is going to be the log difference of output with logged potential output multiplied by 100. So then the output gap that we're about to plot here is strictly in percent terms. It's the percent deviation in output from full employment output. So it's still in a percent terms, which is going to make the calculation of our Taylor rule so easy, because if we do that, then everything in the Taylor rule is a percent, so we don't have to convert it to decimals or anything like that. So this is the output gap as it sits, as measured using Congressional Budget Office estimates of full employment or potential output as a percent deviation from that. So we see a much more stable time series. We see something that reverts back to a zero mean. Around zero, we are fully employed. There are areas, if this graph where we're above zero, which means that we're overemployed, and then there's areas below, the line pops below zero, which means that we're underemployed in those particular areas. We see the most movement of this line, usually in downward shifts, during the red shaded bars here. That kind of indicates exactly what's happening to output in the middle of recessionary phases. But sometimes we'll see recessionary phases happening that are much larger than what the actual identified recession is. So we can see over here in 2001, we had a tiny little blip of a recession. But if we see the peak of what happened, we actually started falling a bit earlier, and then we don't pick back up until a bit later, but the actual recessionary bar doesn't quite match up with that. So there is some degree of I don't want to say measurement error. So maybe the best phrase for that. There's some degree of measurement error here. So like I said, these bars, they're identified by the National Bureau of Economic Research, but the potential output, the potential GDP portion of this, the full employment output portion of this, that is measured by a separate statistical model. And so there's some degree of variance between what we identify as a recession versus what actually is the recession. So keep that in mind as well. Things don't perfectly line up in that regard. So we clearly see kind of a repeated pattern. We see large scale drops, typically though, within most of the recessionary phases. And of course, this is going to just continue to plummet as we move out into this shaded bar for 2020. But we don't have that data here, so we're just going to kind of move on from there. All right. So those same dynamics are going to be present within the Taylor rule calculation, but less so because they have a smaller weight. So again, it's important for us to understand how things are working. This kind of adds a cyclical component to the Taylor rule estimates, but it's not going to be the predominant or underlying dynamic within the Taylor rule. The actual inflation numbers are going to be the major sticking point for the Taylor rule calculations. Great. So let's set some parameters here. And at this point, I'm bothered by this. So give me a few moments. Let's do some housekeeping here. Let's add some comments here. So I mentioned this in the last video. I really like to be neat in my coding. I like to have lots of comments. So we'll load data, and I can actually kill that line here, and then we'll do inflation and output gap plots. Fantastic. And then now we'll down here we'll say set parameters. Now, I'm going to explicitly define the parameters. We don't have to do this in our calculation, but I'm going to do it here because it's good coding practices, and I want to make sure that I'm teaching you guys good coding practices from the very beginning so that you already start to think that way. So if you recall from our calculation of the Taylor rule, and if you're not familiar with the Taylor rule and you're just stumbling across this video on YouTube, maybe reach out to me, shoot me a message or something, and I'll be more than happy to send you something real briefly on the Taylor rule. But there was a parameter RR, which stood for the long run real interest rate. We were going to set that at 2%. We have also an inflation target, pi star. Actually, I'm going to call it pi, and it's not p. We'll call it pi star, and that was also set at 2%. It doesn't have to be set at 2%, but that's assumed to be a constant parameter at 2%, and there's actually a whole bunch of economic literature, of which yours truly has contributed to, that suggests that maybe that pi star is a time-varying process, and then how to extrapolate that from data. But anyway, a little shameless shilling of my own research here. And then we had two parameters, A and B, and they were both set as even values at 0.5, but I'm going to explicitly separate them. I could code that in a couple of different ways, but I'm just going to explicitly call them this number. And the reason why we're going to call these numbers, instead of just plugging these numbers into the calculation that we're going to do here in a minute, is because I want to treat these like individual objects. So that if you want to change the value, all you have to do is change the number, rerun the line, boom, and you have the new weighted policy rule for what you're after here. And so if you automatically think of these things as individual parameter values that you want to play with, treat them as their own objects, and then you refer to their names within the calculation, and it'll help to not only line up your calculation in RStudio with your notes, but at the same time it will also just be good coding practices rather than just starting to plug in numbers directly into our calculation. Great. And so the final thing that we're going to do is we're going to call this Taylor rule object, or this Taylor DataFrame object rather, and we're going to append another column onto this DataFrame. So we're going to use the $, and then I'm going to call in this other column rule here. Now notice rule does not exist in this Taylor DataFrame. We're going to create it. So this is going to be basically appended directly to this existing data frame here. So we'll call this call this column rule, and this is going to be equal to the Taylor rule that we talked about in class. So I'm just going to start building the Taylor rule exactly as it appears in your notes. So we're going to have RR. We need now we need inflation. So we'll have inflation there. We need A times an inflation gap. So again, we'll have Taylor inflation, and then we'll subtract pi star. And actually, this is going to run over, so I'm going to hit enter here and let that auto indent, and I think that should give me enough space. Oops, lowercase b. And then we'll multiply that by Taylor $. Great. So this should look exactly as we have in our calculation of the Taylor rule. So here we have the long run real interest rate. We have the level of inflation with the implied coefficient of 1. We have A times the inflation gap, which again has the level of inflation, minus pi star that we previously defined. And we are also adding then this B parameter times the gap term. Now notice in your notes you had YT minus YTN for output minus natural output, but this is already calculating that gap in percent terms, so you don't have to do anything. You can just call that one column. So fantastic. So we should be able to run this without any errors, and lo and behold we do. And then we can actually go back to our Taylor data frame, and we can now see that, oh yes, we have indeed plotted this new rule. So now we have this column of data. We have our initial interest rate column of data. Let's now put all of these together so that we can examine how the Taylor rule lines up with actual interest rate data. So great. Again, I forgot my comment, so let me put my comment down here. Let's say define Taylor 1993 rule, and then here we will put final plot. All right, and so I'm going to take this that we have up here for our plot. I think it's still on my clipboard, but I'll grab it nonetheless. I'm going to copy it. I'm going to go down here, and we're going to hit paste, and then we're going to edit it from here. So again, we still have the Taylor data frame that we're going to call as our primary data object for the ggplot. We're going to leave the geom_rect commands exactly the way we have, since they don't change one bit for us. The first geom line that we're going to have here, I'm going to put int. And for the int, for the effective federal funds rate, we'll just leave that as black, so we'll leave that unchanged. But then we're going to add another geom line here, and this is going to have AES. For the x-axis, we want date. And then for the y-axis, we want rule. Arrow out of the AES argument, comma, enter again. And here I'm going to define the color as equal to, let's just make it blue. So it's got a nice degree of contrast to it. And then make sure we have the plus sign again. So it wraps onto our labels. Our y-axis is unchanged, our x-axis is unchanged. Title here, now we don't want to leave this as output gap, so here we're going to say US, let's call this effective Fed funds rate, black, and Taylor rule, blue. So that's kind of let me make sure I haven't missed anything. Yeah, so that's kind of an ugly title here. It's a long title, but then it's at least descriptive here. Since we're not organizing this in a tidy way like we did with M1, M2, and MZM, where it automatically will generate a legend for us, it's probably prudent for us to at least specify the colors within the title so that it's at a glance you can see and know exactly what the data is. It's purely semantics. You can do this in multiple different ways. We go to melted the data to have done that, but if you're not going to do that, at least make sure that somewhere in your plot or in your labels you define what line is which, because it just it's just polite. So great, we will execute that and let's see what we get. Ooh, that's pretty. Let's zoom out again so we can oh, hello. Oh, there we are. It was underneath. So we can now see exactly what the Taylor rule says we should have versus what the actual effective Fed funds rate is. So recall the effective Fed funds rate again is going to be in black. So we can see this is as the kind of capturing not only the primary policy movements of the central bank, but also some degree of systemic risk, since this number is allowed to vary to some degree. A little bit less so in current terms. The closer you get to current day, the Fed is really trying to torque down on this rate, so the amount of market movements is somewhat stemmed, although someone from the Fed might arguably disagree with that. But the Taylor rule has much higher degree of volatility to this because of its additional weight that it places on the inflation data. This the Taylor rule in blue, it oscillates around this policy rule much more. It usually calls for, if there's a drop or a small tick down in the data, it's usually more exaggerated. If the data moves up, it tends to be a bit exaggerated again as well. That's because of the underlying data generating process of inflation. But then, of course, also to some degree, what's actually happening with the underlying real economy in terms of output via the output gap. What we do see of particular importance with monetary policy making, as Taylor noted, coming throughout the 1980s and the beginning of the 1990s, this data really it hangs on relatively well with what's happening with the actual interest rate. So there's a lot more line up to this. As we move away from that, we have periods in the early 2000s where for long periods of time we effectively are well over what the central bank is actively doing. And then coming out of the last recession, we hardly ever touch down on what the central bank is actively doing. That's problematic. And so this has led to some very public disagreements among macroeconomists. We have a bad habit of airing our dirty laundry a little bit too much. But it's this last few years, these last 20 years, have seen kind of a marked departure of the central bank away from the classic Taylor rule as dictated by Taylor, which this estimation does its best to do. I'm not sure that Taylor used Congressional Budget Office estimates of natural output in his calculations, but I do know that he advocated strongly for CPI inflation, and of course then the parameter estimates as we've defined here are exactly what he defined in his paper. So so Anyway, we can have a further discussion on this, but at this point now, you're able to at least simulate a policy rule for the central bank, and you can kind of then compare it with actual realized data. Which was the ultimate purpose of this exercise. Thank you so much for watching. If you've got questions, shoot me a message on Slack and I'll get it back to you. If you're watching this somewhere else on the interwebs, then by all means leave a comment below or shoot me a message via YouTube, and I'll get back to you as soon as I can. Thank you so much for watching.